So it sounds, let me use an awkward analogy maybe, it sounds like a bunch of singular north poles of magnets trying to get along together in a crowded room.
Yes.
Is that approximately right? Because you can imagine pushing north poles together. They don't like to come together. They twist around each other. And you can imagine that being compressed together as a consequence of gravitational force. Now, would it be then that there's a probability distribution that those interacting particles are going to actually collide hard enough to fuse? So they're interacting, and now and then the interaction is such that they fuse, and there's some set probability of that increases as temperature and pressure increases.
That's exactly what it is. So it's, and in the end, what happens is you can take this statistical approach to this large distribution of particles that are behaving in. You can't predict an individual particle's probability.
Right.
An enormous ensemble of them, you can start treating them statistically, and that's in fact exactly what we do. We use laboratory measurements of things like, we basically take single particles and find out their probability of interacting at a given energy.
Mm-hmm.
We measure those extremely accurately. And then what we do is we assume that the system is in this deep thermal state. Essentially what's happened is it's maximized its entropy effectively, because they bounced off each other so many times. And then you can statistically describe a probability that actually the particles will fuse. And this probability depends only on the temperature. We call this a rate coefficient to be more technical, but that's okay. It's basically just the probability in an ensemble of these particles that in fact the fusion can occur because of these interactions.
Right, and the denser that medium, the higher the probability that those are going to occur.
So, and then we tend to separate those. There's basically one function, and this is key actually in fusion, which we might get a little bit more into, is that so one of the independent, we consider the independent parameter or the controlling parameter primarily temperature, because it is an absolute requirement. So if you take the most simple fusion reaction, there's minimum temperatures that you can get net energy out of it. It tends to be about for the terrestrial sources, so it's about 45 million degrees Celsius. That depends only on the temperature. So we tend to break it out. There's one part of the reactivity depends on the temperature, and then we separate, and there's another one that depends on the density of the fuel. And this is actually intuitive, right? It's like, so as I increase the density of the fuel and I have fixed probability for an average ensemble of them, I can calculate how many fusion reactions I'll make in that medium in a unit of time and in a fixed volume. So this is really important because this informs us about how much for a terrestrial energy source, how much fusion power, because every time a fusion reaction occurs, it releases energy. So we can actually calculate from this directly the amount of power that we make in a fixed volume of this fuel once we reach those conditions. And it depends on the density of the fuel and the temperature of the fuel. Yeah.
Okay. So now we've explained how this occurs in the sun. We've explained why it isn't a runaway process. We've described the relationship between pressure and temperature, but then we're stuck with the next mystery, which is, well, you don't have the sun on Earth. You don't have that gravitational pressure, that volume of hydrogen. How do you duplicate the conditions that are necessary to produce fusion? How do you produce temperatures approximating, you said 45 million degrees? It's an unimaginable temperature. It's no wonder that things cool down when a fusion reaction would cool down if it touches anything earthly, because that would be like plunging it into the most frigid deep freeze imaginable. So how do you duplicate these conditions, however temporarily on Earth? You do something like make these electromagnetic containers, and I know that you use laser beams to increase the density, but maybe you can walk us through the construction of the electromagnetic container, what technical innovations that's dependent on, and then how you attain those temperatures and pressures.
Right.